Hello, welcome. This is Kjell Fritz, and we will continue with our application of general relativity in our framework, which is in the low velocity weak interaction scheme, where all experimental predictions have been done for general relativity. And we will use our force formula that was derived by Einstein. And last time we checked the gravitomagnetism through parallel motion, not observable. But what is observable is the perihelion shift, which is a gravito-inductive phenomenon. And we derived the proper formula for that. Today, we will look into Lense-Thirring Frame Dragging effect and derive the correct general relativistic prediction for that. And we will compare the prediction with the satellite experiment gravitation probe B, which also measured a complementary effect, which is most likely, I'm not 100% sure yet, but most likely a gravito-inductive effect. And we will not derive that, just comment on this qualitatively, but we will derive Lense-Thirring Frame Dragging effect in this presentation. So what we do is to apply this formula here, which was derived by Einstein in his book, The Meaning of Relativity. It's a vector formula, and it contains a static term, gravito-magnetic term, that means velocity dependent, and a gravito-inductive term, which is the acceleration dependent term here, is the force on number 2, so it depends on acceleration of number 1. We have both velocities here. So it's a force formula, so it's a mutual interaction between two objects. And we have a similar formula in electrodynamics, and that's very important because what we will do when we derive a Lense-Thirring effect is to use the corresponding formula from electrodynamics and then convert it to general relativity, that is gravitation. And we see from this formula here what we have to do then is to change charge to mass. We have to change 1/4 pi epsilon 0 to gravitational constant g. Also, we have this important factor 4 here, and we also have to take notice of that the terms are of opposite sign. So then this we did last time, gravitomagnetic effect theoretically, because this has not been observed for gravitation. And then last time we studied the perihelion shift, and we derived the correct formula for this shift and within our framework. And this formula is given here for the force. And this has not been done before, so it's an important verification of our method. Einstein started from the approximate Schwarzschild metric and assumed sun to be static, whereas we have to accept that sun is not static but oscillate around a center of mass. This was last time, so now come to this application. Lense-Thirring Frame Dragging. Again, we start from Einstein's formula, which we take over to this slide. So what happens, what kind of phenomenon is that? That is, we consider a circulating mass current as object number 1. And this in our experiment, that will be a spinning planet. So then Lense-Thirring found that space-time is dragged with the rotation. So Lense-Thirring worked with this space-time metric and considered space-time. However, our intention is to work with concrete things, so we put an object here. We let the object, in this case, approach the rotating mass current. So the object is this object is then number 2, so this is the force on number 2. And then we have these vectors to handle in our formula. So we can have a look at this green one as acceleration dependent. We have an acceleration here, it's a centripetal acceleration. And we consider the nearest mass elements. So this one is a centripetal accelerated to the left. So we will get a inductive force on object number 2. But this is directed opposite the distance vector. And that's not what we are interested in here. Not in this case for frame dragging, because this is a gravito-magnetic effect. So look at this red one here. V1 and V2 are perpendicular, so this term here vanish. There, so we then get this formula here. Then we see this magnetic formula, since V2 and R oppositely directed, this will give a negative sign. And together with that negative sign there, we get a force in the direction of the mass element, number 1 here. So in the direction of this velocity, v1. So that will give this effect that the Lense-Thirring calls frame dragging. The object will start to co-rotate with the mass current. So that is what happens. This has not been observed. You can think of using Earth as the mass, a spinning Earth as a circulating mass current, and then sending an object towards the Earth, and then to check if this force will appear. But that will be much too small effect, so it's not observable. However, theoretically, this is interesting because we have the same kind of phenomenon in electrodynamics. So now we will compare with electrodynamics. Then we can use a current carrying loop. And we then have the object here with a negative charge to get the exact correspondence with this gravitational phenomenon. Because the current are positive charges, and we have attraction between, in gravitation, we have attraction between mass elements. So to get an attraction then between this current element and the negative charge here, to get attraction, this charge has to be negative. So then in electrodynamics, we are used to working with fields. I don't know why, but this is a tradition which complicates things, of course, but we are used to it. So we introduce a magnetic field here pointing into the plane, and then we use the Lorentz force. And then we see with the negative sign of Q2 here that we generate a force in the same direction as V1 here. So this we do already at high school. We learn to do these things. So in gravitation, the mathematical treatment is equivalent. You can also introduce a gravitomagnetic field there if you like. If you like to complicate things, you can do that. And then you can derive a Lorentz force if you like to complicate things. And then you can do that, and you find a gravitomagnetic force in this direction. So relativity is not more complicated than electrodynamics. And since we do this in high school, we should also be able to do the corresponding gravitational phenomena at high school. That's why I say that this approach to general relativity that I present here is really valuable in a deductive perspective, because it's open up the possibilities for high school to introduce general relativity. And it's of course easy to observe this phenomena in electrodynamics. You just take an electron beam and direct it towards the current carrying loop. And then you see this directly, this force. So this is an eminent phenomena to study, and then to compare it with the equivalent phenomenon in gravitation. However, we look for an experiment where this phenomenon can be observed. So that is the gravitomagnetic effect. And that to do that, actually, it has been done by this experiment Gravity Probe B. And for the circulating mass current, the spinning Earth is used. So this is replaced by the spinning Earth. And instead of having a translational velocity here, we have a sphere which is spinning. So then what we study is the spin interaction. And that is then what is called frame dragging by some reason. It's also here, the language is of historical origin. So it looks like this, the experiment. We put these spherical objects, which are rotating, spinning, on a satellite. And then we look for the interaction with the spinning Earth. That will give us a spin interaction. The spin of Earth is fixed. These spinning objects on the satellites are free to rotate. So they are kept free. So there is no friction, minimized friction. And then what we then expect is a precession. So a spin-spin interaction gives a precession. And this is a phenomena which is 100% equivalent to the electrodynamic Larmor, so-called Larmor precession. We have this fixed magnetic moment in that case here, and then another magnetic moment here, and that moment which is free to move will precess around the fixed moment, so around this spin vector. And it's this precession that is measurable, so it's large enough to be measured. So we compare this with electrodynamics. We know that in our approach, electromagnetism and gravitation are equivalent. In electrodynamics, we have one fixed magnetic moment, which is a spin vector, which is, for example, caused by a current carrying loop. So that is equivalent to the Earth, the spinning Earth. And then we have another magnetic moment, which could be a spinning particle, spinning electron, or a nucleus. And then we observe a precession of this magnetic moment around the direction of the fixed spin vector number 1. That is Larmor precession. And this is due to a torque. This object number 1 causes a torque on object number 2. So nothing else can cause this precession than a torque. So instead of force, we work with torque. Torque on number 2 due to number 1. Torque on number 2 here due to the spinning Earth. In order to get the general relativistic formula, we'll then use our recipe when going from electrodynamics to general relativity. So we take the well-established formula in electrodynamics for Larmor precession, and we convert it using our recipe to general relativity. So this will form a very elegant demonstration of this recipe. And of course, we know the result because it has been derived in different ways before. So if we get a result which agrees with what we already know, then this is also a nice verification of our approach to general relativity. So then we start with electrodynamics, and this is a classical formula for the interaction between two magnetic moments, M1 and M2, and that this is the torque on object number 2. This is derived, for example, in my book, but in any book in electrodynamics or electromagnetism or what we choose to call it. But it's field-free. So it's very attractive for me in my book here because that was my approach. So it's a lovely formula, the interaction between two magnetic dipoles. So it's a dipole moment, M1 and M2. We have the same formula for electric dipole-dipole interaction, which is very important because that's how nature interacts electrically. And the electric force is a dominant force in nature. It's not the magnetic force, it's the electric force. But free charges are rare, so mostly nature interacts through molecules. And molecules are electric dipoles. So it's a dipole-dipole interaction electrically, which is the fundamental interaction in nature. And the electric dipole-dipole formula has the same structure. We just replace magnetic dipole moment with electric dipole moment. And that is also shown in my book. So this dipole-dipole interaction formula is very important. And not only torque, but also the force, the corresponding force formula. So what you see here is that interaction between free charges, and we have 1 over distance squared, but the interaction between two dipoles, it's 1 over distance cubed dependent. So here, something containing object number 1 between brackets, but there's a scalar product with r hat. Now distance, change distance now, notated small r. So that is small r here. For our gravitation, it's a distance from Earth's center to the spinning sphere on the satellite. And that small r appear here, and that is a property then the scalar product is then dependent on object number 2. So it's dependent on the position of object number 2. Then we apply our recipe, change this 1 over 4 pi epsilon 0 to gravitation constant. We also have a factor of 4 larger kinematic correction in GR. And this is, of course, a kinematic correction. This is magnetism, it's motion, the spin, so it's motion. And we then we should replace charge with mass, and this time we should replace magnetic moment with gravito magnetic moment. And then we shall convert to spin, and when we do that in electrodynamics, we multiply the spin vector with this gyromagnetic ratio to get the magnetic moment. And that is charge over 2 over mass. Now we replace charge with mass, so gyromagnetic ratio will become 1/2. So that's why we have 1/2 here. And it appears twice, so both for number 1 and number 2, so we get 1 over 4. But we have a kinematic correction with the factor 4, so that will cancel. So no factor 4 or 1 over 4 remain in our final formula. So here is the general relativistic torque for a spin-spin interaction. Spin number 1 here, spin number 2 here. 1 over distance cube, 1 over c squared, as in electrodynamics, and the coupling constant here. So the structure is almost identical. And then we cannot measure torque, we cannot measure force, we can only measure the consequence of it. The consequence of a torque is a precession. How do we get precession out of this? That is the easy part of this calculation, because it's given by this formula. And then we can just read, this is a kinematical formula which we do not motivate. You can find it in any book on mechanics. And then we just read off the precession rate. So that's capital omega, so it's something with a dimension 1 over second. So it's the angular velocity of the precession rate. How many radians per second? So it's radian per second. So we read it directly from this formula. So we get the precession rate here predicted from general relativity. So this is the formula that this experiment, gravity probe B, applied. Made a calculation and checked the number. Would this be possible to measure? They found an experimental method, and they found that it would be possible to measure if we do it accurately. What they have to do to estimate the general relativity prediction is to integrate over a full orbit, because the spinning spheres, they are placed on a satellite. There are 5 of them, and the satellite has to be put in an orbit, of course. And so the distance vector here, mainly the direction between distance vector and the Earth's spin vector, change it with position. So one has to integrate this formula over a full orbit. Also, if Earth had been exactly spherical, then this is the expression for the spin vector. So this is moment of inertia, and this is the angular velocity of the Earth spinning. This is the moment of inertia for a perfect sphere. But this experiment has to correct also for the fact that Earth is not exactly spherical. So there are some corrections that has to be done, but that is rather straightforward. So we can have a look at that experiment finally. This is a picture from their official website, which also describes the experiment in detail. There were 5 of these exactly spherical objects, and they were set in rotation, so spinning. The spinning vector at the start is in the orbital plane. And the frame dragging effect, gravito-magnetic effect, which I call it, the spin-spin interaction, it's also by these guys, is officially called frame dragging, so it's a historical expression, was predicted to be this small amount. So they put this into they measured, they let it orbit 5 times around Earth. They could then obtain a predicted value of general relativity and compare it to what they measured. So in this direction, we have the gravito-magnetic effect due to the torque that arises due to spin-spin interaction between this small spherical object and the Earth. And remarkably, they found a perfect agreement with general relativity within 10%. So that is truly remarkable. However, what is more remarkable is the complementary effect, which they call the geodetic effect. That we have not discussed here, and I have not worked it out fully. I just done it qualitatively and found that this is, in our perspective, this should be referred to as the gravito-inductive effect, and it's very similar to the perihelion shift. And the reason is that this spinning sphere on the opposite side, they will orbit with different speeds. So the opposite sides here will exhibit a different centripetal force, and that will cause, in equivalent to our analysis of the perihelion shift, that will cause a different inductive force on the opposite side, which will then in turn cause a torque. So that is my hypothesis. Qualitatively, it works, but I have not checked it numerically or quantitatively. However, these guys have derived it with the traditional way, with the starting from the space-time metric, and also so that can be predicted in that way, and they found a perfect agreement with general relativity for this complementary precession in the perpendicular direction. So this is an advanced experiment. I have a background in particle physics and done experiments at DESY and CERN, but I must say I've never seen anything such advanced as this. And they also find a perfect agreement with general relativity. So I wonder what is the Nobel Prize Committee waiting for, really. This is extraordinary. So that was all for this time. Thank you very much for listening. Bye-bye.